Hello guys, Marcio Marinho here, welcome back. It's time to talk about recursion. From this point on, I'll be showing a lot of code. Then I thought it would be nice to ask you to not memorize any code at all, but instead of doing that, try to understand what the algorithm does, which means its mechanics, how it does, and why it does on the way I'm presenting to you. Because this knowledge will be way more important to absorb than simply memorizing any piece of code. Because the code will simply follow that structure or that idea the algorithm is presenting. And you'll be able to port that algorithm or data structure to any other programming language you want to code. And if you like my channel and my videos, please subscribe to my channel, like and share my videos. So it's time, let's do this. Recursion, part 1. But what exactly is recursion? I brought here a formal definition, but we can really simplify this whole definition saying that recursion is a function calling itself. And in order to do the work, we need these three properties: a base case, which means where the recursive calls will end. Second one is a set of rules that reduce all cases to the base case, which means we'll be simplifying the problem on every recursive call. And the third one is the ability to call itself. Java has all these properties, as you can see here in this example. In this first line here, I am showing how to multiply two numbers on the obvious way. 2 times 3 equals to 6. And the second one, I'm showing the recursive way of doing the work, which is basically summing number 2 3 times. That's why I have this function here with the base number, which is true, and the n, or size, or n times, or how many times I'm going to sum the number 2 in order to produce the result, which is 6. In the first line of this recursive method, I have a check. If n equals to 0, then return 0. This one is my base case, and we cannot live without it. That's extremely important. This point is where the recursion ends. And the second and last line here in this method, I'm simply summing the base case plus another call to multiply, passing the base number, which is 2, and n minus 1, which means I'll be simplifying the problem here. I'm passing here 3 minus 1, then the next call 2 minus 1, 1 minus 1, until I get 0, and then this is where my recursion ends. That's my base case. Let's not forget that. Time complex of this algorithm is O of n, because we are going n times. And space complexity is always O of n, because we're spending more space on the recursive calls, because we need to recurse n times until we get to the base case. So another example here is I have the entry point, multiply 2 times 3. This is my entry point. I do the first recursive call, which gets multiplied 2 and 2. I recurse again to the second recursive call, multiply 2 and 1. See how I am simplifying the problem. That is the second property. I'm reducing my problem. Then multiply 2 and 0 on the third recursive call, where I hit my base case because n is equals to 0. Then the recursion will return 0, which is the base case. Then the second recursive call will also return. So it will return 2 because it's summed 2 plus 0, which is equals to the first recursive call, which will also return 4, that's 2 plus 2. And the entry point will also return 4 plus 2, which is equals to 6. And this is the depth of my recursion. We have 3 recursive calls. Once it hits the base case, which n is equals to 0, it will return the calls to the previous caller method. It's a depth 3. And because of the recursion stack, we will spend space proportional to n, which in this case is 3. Again, the base case is very important. If we forget that, we'll get the infamous Stack Overflow, because our code will keep going forever until we have exhausted all the stack space. So don't forget the base case. Another example is the factorial. In mathematics, the factorial of a non-negative integer is denoted by n exclamation mark, which is simply the product of all positive integers less than or equals to n. Sounds complicated, but it's not. For example, 5 factorial is equals to 5 times 4 times 3 times 2 times 1, which is equals to 120. That's exactly what this text is saying. 5 factorial, just 5 until it hits 1. Or 6 factorial, 6 times 5 times 4 times 3 times 2 times 1, and so on. This is the factorial. We can also make a recursive factorial. That's how this example works. I want to have a factorial of 5. This class has exactly the same structure as the previous one. We have a recursive method here. This time we receive only one parameter. If we hit 1, which is our base case, as you can see here, the factorial finishes when it hits the number 1. Then we simply return 1. And the second line, we simply multiply the number times factorial of the number minus 1. So number times factorial minus 1 until we reach the number 1. That's exactly what it does. And it works on the same way as the recursive multiply. It goes using the stack. Time complexity is O of n, and space complexity is also O of n. So here we are reducing the problem because we have a problem size of n, and then we multiply n times n minus 1. That's all this method is doing. And now it's time for our demo. Sit tight. Let's see how in this demo how the recursive call works on the stack. I have here 2 and 3. Recurses 2 and 2. Recurse again 2 and 1. Recurse to 0. Base case returns 0, returns 2, returns 4, and then returns 6. That's exactly how we've seen that before. Okay, let's also take a look at the factorial example. It's pretty similar. A factorial of 5, 5 minus 1 recurses, 4 minus 1 recurses 3, 3 minus 1 2, 2 minus 1 1, and it returns 1, returns 2, 6, for 420. That's all what the recursion does. On every call, we reduce the problem, and then we may or may not return something. In this case, we return the number we received for that factorial. Let's run our recursive multiply. This is the same code as the one we have in the slides. I'm going to place a few breakpoints here so we can go step by step in the algorithm and see what it's doing. So let's debug. The first line here is the, let's say, normal multiply, 2 times 3. And here, as you can see, the console log. 2 times 3, just shoot straight 6. Now we're going inside our recursive multiply. Is the function. Here is our base case. And then we recurse until n is equal to 0. So let's go. First time n is equal to 3. As you can see here, n is 3. We recurse one more time, n minus 1, which means 3 minus 1, which means n now is equals to 2. It's not equals to 0. Then we go again, n minus 1, 2 minus 1, n equals 1, and it's not 0 yet. We'll do one more time, n minus 1, which means 1 minus 1 will be equals 0. Yeah, n is equals 0. So this is the base case. This is the point where we are going to return. As you can see here, here is the recursion stack. So this is the entry point, and then all the times I have recursed until reaching n equals to 0. So that's pretty simple what it does. Now I'm going to return 0. Then we'll pop this entry from the stack. That's it, just pop it. And then we are going to sum the base, which is 2, plus the result. And we keep doing that until we get to the last entry, as we saw on the slides in the visual graph. So we keep popping, and then we got to the last one, which we return to the first function call. And that's it. Recursive multiply equals to 6. We just returned from our recursion. And that's all what our code does. It keeps going down, recursing, simplifying the problem, which in this case is n minus 1, until it reaches 0. Then it returns, and then sum 2 plus whatever it returns. This is the first example. Our second example is the factorial number, which is very similar problem as we had before, but this time instead of simply passing two parameters, we are passing a single parameter, because what we're gonna do is 5 factorial equals to 5 times 4 times 3 times 2 times 1. And this is exactly what we are doing here in this function. So the base case is 1. Once we reach 1, we return, which is the last time we have to recurse. And here we simply multiply whatever n at that moment is times n minus 1. So 5 times 4, which is n minus 1. Next time we recurse 4 times 3, and on and on. I'm just going to put a breakpoint here so we can trace this one as well. That's it. That's the first call, n equals 5. Then we are going to call n times factorial, n minus 1. See, n minus 1. Let's evaluate the expression. N minus 1 equals to 4, because n is 5. We'll keep recursing until we get to 1. So let's do this. Recurse again, n equals 4. And pay attention to the recursion stack here. So it's gonna grow until it reach 1. Okay, that's it. N equals 3. N equals 2. And n equals 1. So that's the base case. N equals 1, return 1. And then n equals 2. It's gonna be 2 times 1, 2. And we keep doing that until we pop all elements from the stack and return to the main function, which gives us 120. That's the value we want. That's all what this recursive code does. It's pretty simple and pretty straightforward. Okay, that's it. So we just finished the recursion part 1. I hope you have enjoyed, and I'll see you on recursion part 2.